Okay, so this is lecture 10, balancing equations. So it's an introduction to molecular equations and how to balance them and what that means. So go to the slides. The lecture slides are in module 7 under reactions and stoichiometry is the title. It's at the bottom. Okay, so we talked about the beginning of our journey here with the scientific processes, the scientific method, a little bit of the history, what is matter. Then we got introduced to the alphabet of chemistry, which is atoms and the periodic table. And now we moved into words, which are the molecules and your molecular formula, stoichiometry, molar ratios, using the mole to convert items. And then, of course, we just finished structure. So now we're moving into reactions, and we're going to put all of these together into sentences, chemical sentences, which are reaction equations. And there's a specific way they have to be written. But this is the beginning of the fun stuff, in my opinion. All right. So what is a chemical reaction? Very important. Remember I talked about chemical change, physical change versus chemical change. This is along the same lines. A chemical reaction is when the product is different from the reactant, which is your starting material. So in a chemical reaction, your atoms are rearranged to make a different product, a different molecule. And now that you've done structures, you see a little bit more of how the arrangement makes all the difference in the world of a molecule, its chemical characteristics, its physical characteristics, etc. So chemical reaction is defined by the conversion of one substance or set of substances, so your starting material, into another. Your product, at least one thing on your product has to be different for it to be a chemical reaction. Our definitions, the reactant is the left side. It's your starting material. Everything on the left side is reactant. Product is what you're making. That's on the right side of the equation. Very important. The products differ from the reactants only in the arrangement of the atoms. So you're not losing or gaining any atoms. You're not losing or gaining any matter. It's just being rearranged. So here you have a precipitation reaction. These two solutions are being merged, being combined, and you end up with this blue precipitate. A precipitate means something that has a solid that's formed in a liquid from a chemical reaction. It precipitates. We also say it falls out of solution. So how do you know that a chemical reaction has occurred? Well, the only way to really know is to test it scientifically, or to know what the chemical equation is, and then you know what to expect. But some indicators of a chemical reaction are a change in color. You create smoke or vapor. Now be careful, because that can also be a physical change, right? Maybe you're just changing the phases. So these are indications of possible chemical reaction. You're generating heat. Again, we have color and smoke. You generate a solid. This is actually this cloudiness is actually tiny little particles that have formed when you mixed two liquids, two solutions. And of course, fire, gas again, bubbling. So these are all indications of a possible chemical reaction. And this is the same thing in, a metal coating. You have metal forming a coating on something you've put in there, or on your flask. But remember, it doesn't guarantee that this is a chemical reaction. This is just potential. But you see this, there's a really good chance you had a chemical reaction. So going back to our microscopic view, this is what you see. So there's a chemical reaction possibly there, right? at a molecule level, what's happening? And this is forming vapor, forming water vapor. So you started out with hydrogen gas and oxygen gas, and you made this new molecule of water. It happens to be in the vapor form, the gas form. Our sentence says this, and this actually says a tremendous amount of information. It says that hydrogen gas was mixed with oxygen gas to form this molecule, water. Now, there's a problem here. This is not balanced. Yeah. Because if you notice, I have two hydrogens over here, and I have two hydrogens over here. That's fine. But I have two oxygens here. I only have one here. So we actually, this is an unfinished equation. We will have to balance this equation. So I'm going to use this as my simplest example of balancing equations. So I'm going to be on the whiteboard a lot this lecture. So you have H2, and that's a gas, and O2. When we say yields, it's one of our terminology, H2O. So I have two hydrogens on this side and two on this side. So that's fine. But I have two oxygens over here, and I only have one. So you have to use a coefficient. I have to put a 2 in front of this. So now I have two water molecules, and I now have two oxygens. You multiply this 2 times everything in the molecule, but I now have 4 hydrogen atoms. So now we have to come over here and make 4 hydrogen atoms on this side by putting a 2 in front of that. So now you double check. I have 4 hydrogen atoms on this side, 2 times 2, 2 times 2 here. So I have 4 and I have 2 oxygen. So now it's balanced. That's a completed equation. So basically I have, 2 hydrogen gas molecules here plus 1 oxygen gas molecule yields two of these, 2 waters. So 1, 2, 3, 4 hydrogen atoms, 1, 2, 3, 4, 2 oxygen atoms, 1, 2. Okay, they're just rearranged. So you have to have the correct number, the same number of atoms on the left side and on the right side. That's called balancing equations. And that is what this lecture, what I'm going to work through here quite a bit. All right, back to the slides. So the chemical equation, it's a symbolic representation of a chemical reaction. You can actually say a tremendous amount of information with a chemical equation, a reaction equation. And there are very important parts of every reaction. You have the chemical formulas, right? We had H2 and O2 and H2O. You have to say the physical states of everything in there. In the whiteboard reaction, and you can go back and look, or I'll go back here. See the G, that means gas. You have to put the physical state. Now, for some of your exercises for balancing, you won't have the physical state because the focus is on the balancing. But when you're writing a complete full equation, and as we go on in this course, you're going to be doing that, you have to put the phase in as well. It's actually very important. And then the ratios. The ratios are the coefficients. That's the number I put at the very beginning of my hydrogen gas and my water to make everything mix. Those are the ratios. So it's 2 moles of hydrogen gas for every 1 mole of oxygen gas to give me 2 moles of water. Is another way you can read that. Sometimes we put the special conditions in. So if energy was needed to make, if you did a reverse of that reaction and you split the water, you would require energy. So you might say, if we did the reverse of this, and actually usually it's done with liquid water, converting back to hydrogen gas and oxygen gas, we might put an E up here for energy. Sometimes you'll put heat in on either side, and we will get to a point where we'll have you do a little bit. So in this course, if you're expected to write heat as part of the equation, you'll be told. So you don't have to try to guess when do I do this, when do I not. But oftentimes you will see either over the arrow, heat or energy, or as part of the equation. All right, so I know this looks like a mess, but take it step by step. This arrow here, extent of reaction, we're not going to get into that in this course, this semester, but at some point you will, and it has to do with the size of the arrow, and usually it's when you have a double arrow, which you'll get into in a bit. You'll show one side goes greater than the other side, but we're not going to do extent of reaction with the arrows this semester. So you have coefficients. That's the number of moles of each molecule or atom or compound needed to balance your reaction. So in this balanced reaction, I have 2 moles of C8H18, I think that's octane, when mixed with 25 moles of oxygen gas, produces 16 moles of carbon dioxide gas, 18 moles of water vapor. And it's exothermic because the energy is on the right-hand side. That means that energy was actually a product. So it also releases heat when this happens. We have physical states here. So this is a liquid with a gas, and this is a gas and a gas. This is your reactant, see? These are your products. So these are the things that you'll be putting into your, well, particularly the molar ratio or the coefficients, physical states, you'll be putting into your equations. So here's an example, and we're going to balance this equation. But if you say with words, when you mix a powdered mixture, so this is powdered means it's a solid. So you have powdered mixture of aluminum metal and iron 3 oxide, and you mix them together and heat it, you get liquid iron and solid aluminum oxide. And so those are the words, and here's the same sentence using chemical terminology. Solid aluminum metal and solid iron 3 oxide. We know that because of the subscripts here, that when mixed together with heat forms solid aluminum oxide and liquid iron. That's the same paragraph, but it's in this reaction equation, and yet I just read it as the same thing. So there's a tremendous amount of information mixed, contained in this. However, this is not balanced, is it? I have 2 aluminums over here. I have 1 over here. So that already tells you this is not balanced. Now notice we don't put a 1 subscript. We only put, or coefficient. We only put if it's more than 1. So I'm going to go back to the whiteboard. So The reaction, so this is your skeleton reaction or your core reaction, right? It's not balanced. And I always run out of room. Let me start over and try to write it smaller. So we have solid aluminum plus iron 3 oxide, solid, mixed together. I'm not going to put the heat in there because this is for balancing. Let's see, aluminum oxide. I don't know if the little window with me in it gets in the way or if you guys can move that. So I'll move it. Plus, I still don't have room. Iron, liquid iron. You can't see that. All right. The first thing you do when you're balancing equations, and I recommend you get in the habit of this every time, is you write down on the left and the right what you have. Now, I do it separately, left side, right side. Some people go down the middle, whatever works for you. So on my left side, my reactant side, I have aluminum, I have iron, and I have oxygen. All right. How many do I have at the starting? I have 1 aluminum, I have 2 iron, and I have 3 oxygen, right? Because you're subscripts. Over here, I have 2 aluminum, I have 3 oxygen. Be careful when you put your numbers in. It's really easy to just go bing, 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 but they're not in the same order as what I wrote. So double check that. And 1 iron. All right, let's start with the aluminum. I have 2 here and I have 1 here. So I have to multiply this times 2. And I put it up in the corner until I'm done because sometimes you have to go back and do this multiple times. So now what do I have? I have 2 aluminum. Since nothing else is in this molecule, I'm only changing the aluminum. Otherwise, I actually go back and I change every single one. Okay, what's the next one? I have 2 iron and I have 1 iron over here. So I'll put a 2 up here. Okay, so this actually, and so I'll make my coefficients bigger. So now that's balanced. Now I have the same number. I have 2 aluminums on each side. I have 2 irons on each side, and I have 3 oxygens. Didn't have to change the oxygens. So now it's balanced. So I'm going to go back to the slides. And here's a visual representation of the steps I just took. So the original unbalanced equation, right? You had 1 aluminum atom on this side, 2 on this side. So this shows your starting number of atoms on each side. Notice we're breaking this down into the individual atoms. You're balancing the atoms, even if they're in a molecule. Because the number of atoms you start with has got to equal the number of atoms you end up with. So you have to get your molar ratios correct. So, and here's a visual representation of putting a 2 in front of the aluminum, right? We increase the aluminum and we increase the iron. So here's your balanced equation. So let's look at this question. We have a paragraph, and it says when methane, which is CH4, gas, reacts with oxygen gas in the air, it combusts, that means it blows up, to form water vapor and the gas carbon dioxide. So here's our starting our reactants, methane and oxygen, both gases. Here's our products, water and carbon dioxide, both gases. Water vapor is a gas. So which reaction equation describes that you would read to say the same thing? Well, first of all, the reactants have to be methane and oxygen. So it's not B, because B is written backwards. The second, okay, and these are all gas. Methane and oxygen are all gas for the rest of them. So A, C, D, and E. What are my products? Water, vapor, so that's water gas, and carbon dioxide gas, CO2. So this is water and carbon dioxide. This is a liquid water, so it's not that. This is water and carbon dioxide gas. Okay, so so A, D, and E have the right reactants. Oh, wait a minute. E is wrong because it's oxygen atom, not oxygen gas. Oxygen gas is O2. So A has the correct reactants and products and physical states. And D has the same. So which of these is correct? We have to go in and make sure we have the same number of atoms on the left side as on the right side. So for here, we have 2 oxygens on the left side and 2 plus 1, 3 on the right side. So that's not balanced. But here, I have 4 oxygens on the left side, 2 oxygens here, plus 2 oxygens here. So I have 4 oxygens on the right side. I have 1 carbon, and I have 1 carbon. I have 4 hydrogens, and I have 2 times 2, I have 4 hydrogens. So the answer is D, because that is balanced, and everything in the reaction equation describes exactly what these words say. So you see, this simple sentence says the same thing as this paragraph up here. So that is a simple phrase that you're going to start learning to speak. So when you're balancing equations, of course, first thing is you have to make sure you write their correct molecules down. If you're given words, this is where the naming comes in. You have to know your naming, because if you don't write the correct molecule down, then you're not going to be able to balance it correctly or get the right reaction. So you write your core reaction down, and then you do your inventory list underneath it, and you start making changes to balance everything. And I'm going to work through a number of examples. If you have one that's by itself, like in the previous example, we had aluminum by itself and iron by itself, it's best to leave those till the last, because they are the easiest ones. And oxygen is often going to be there by itself, oxygen gas. And that's a good one to leave till the very last, because it's usually involved in other molecules. And so it's the easiest to do as your last balance step. All right, that'll make sense in a minute. So I'm now going to just work through a number of these equations. And then really after that, it's just a matter of practicing. So go back to the whiteboard, and hopefully I can not run out of too much room. Trying to get a little more whiteboard space. Okay. So we have on that slide I just left, it says balance the following equations. And it says you have words. Potassium chlorate yields potassium chloride plus oxygen. And if my picture is covering up the word there, that's oxygen over there. But again, this is the slide. You can go back and look at the slide. So first of all, you're going to get this. You have to know what potassium chlorate is. What potassium chloride is. And oxygen is oxygen gas, and I should have said that. Anytime you see oxygen by itself in an equation, it's oxygen gas. You're not going to have a single oxygen atom there. It's too reactive. So actually, I am going to go back to this slide because it's a multiple choice. All right, so potassium chlorate, potassium chloride. So the first thing is stop this and write down what you think the answer is. All right, so potassium chlorate is this. And then you check and make sure everything's balanced. So we have 2 potassiums here and 2 potassiums here. I have 2 chlorines here and 2 chlorines here. I have 2 times 3 is 6 oxygens here. I have 3 times 2 is 6 oxygens here. So when you're multiplying it times the subscript. All right, that actually was easy. Let's do these examples. So the first one is carbon disulfide plus chlorine gas. That's a G. Carbon tetrachloride. And hopefully, so this is one line. Because I didn't know if you could see this on the side or not. All right, first thing I'm going to do is do my inventory. All right, I'm gonna try to rewrite this. This is where I really need the big board. Okay. So the first thing I do is my inventory. Carbon over here, sulfur, chlorine. Like I said, some people go down the middle, that's fine. I like to go left and right. It's one of those situations where you do whatever is most comfortable for you. So how many carbons do I have here? I have 1, and that's it. I have 2 sulfurs, and I have 2 chlorines. What about over here? I have 1 carbon. I have 4 chlorines here and 2 here. And when I have that, I write it out separately so that when I have to balance, I know I have 2 different molecules to balance. It makes a difference. And then I have 2 tin, right? 4, 5, 6, 2. Okay. So the chlorine is all by itself. So I'm going to leave that for last. That's the easiest to do. My sulfur's fine, my carbon's fine. Okay, well, it looks like chlorine is the one I have to change. Well, that's going to be really easy. My carbon is the same, and my sulfurs are the same. I keep checking to see if okay. So I have 6 chlorines here, so I simply need to put a 3 in front of that one. 3 times 2 is 6, and that's all you have to do to balance that. So that one was easy. All right, let's go another one. So I have solid iron plus water vapor That's a G. All right. So again, my inventory. Go away. Here, this little bug wants to do chemistry. Iron, hydrogen, oxygen, iron, hydrogen, oxygen. Okay. I have 1 iron, I have 2 hydrogens, and I have 1 oxygen. Over here, I have 3 iron. I have, see, I almost wrote my oxygen here, but my oxygen is down here. So watch for that. And 2 hydrogen. Okay. So again, my iron is alone, so I will do that last. And also the hydrogen is alone. So we'll start with the oxygen. I have 4 over here. I need 4 over here, so put the 4 over the water. So now what I do is I actually rewrite this whole thing. 2 times 4 is 8, right? And 4. Okay, that's my new count. So my oxygens are done so far. I have 2 hydrogens over here. I have 8 over here, so I need to put a 4 there. And since that's the only thing that changed, I'll just do this. I rewrote this because it's a molecule. It changed more than 1. So now my hydrogens are done. I have 3 irons over here. I have 1 over here. I put a 3 in front of that. Again, that's the only thing that changed. So now I'm going to double check. 3 irons, 8 hydrogens, 4 oxygens. Yes, always double check. So that's balanced with a 3, a 4, and a 4 over there. Okay. Okay. So the next one is a combustion reaction. You will see a lot of these because they tend to involve a bit more back and forth. So C2, I don't remember what it's called. I usually just call them hydrocarbons. That's a hydrocarbon. CO2, that's a gas. H2O, liquid water. So that's H2O there. All right. So let's do an inventory. I have carbon, I have hydrogen, and I have oxygen. I have 2 carbons. I have 6 hydrogens, and I have 2 oxygens. Over here, I have 1 carbon. I have 2 hydrogens, and I have 2 plus 1, 3 oxygens. Again, I do that so that if I have to multiply something, if you just say 3, you're trying to turn 3 into whatever this number is instead of separate molecules. All right, so I'll start with my carbon. So I'm going to put a 2 here. And so now I have 2 carbon. I still have 2 hydrogens. And I have 4 plus 1. I have 5 oxygens. Okay. I have 6 hydrogens over here. I only have 2 over here. So I have to multiply this times 3. And now I've changed and I have no room. So how am I going to do this? All right, let me just try to move over. So I still have 2 carbons. I now have 6 hydrogens. I have 2 times 2 is 4 plus 3. I have 7 oxygens. All right. My carbons balance. My hydrogens balance. The only thing left is my oxygens. I have an odd number. I have a 7. I need to turn this into 7. Well, how do we turn 2 into 7? Because it's a subscript. We multiply it times 7 halves, right? Because then my 2 is going to cancel out and I have a 7 there. So I actually am going to put 7 over 2 as that coefficient. That will give me balanced. I now have balanced my oxygens. But we don't use fractions, do we, in chemistry? You can't leave it like that. And this is what you do. You get this a lot with combustion reactions. You can get rid of that 2 as a coefficient by multiplying by 2. I know it sounds like there's a lot of 2's. This is here so we can turn this oxygen gas into a 7. 7 total oxygens. But we can't keep that 7 halves there. And you can think of it as 3.5 as well. That's fine. You multiply the entire reaction, because what you can't do something to just 1, because this is now balanced, times 2. So when you do that, you put a 2 in front of this. 2 times 7 over 2 is 7. Two times 2 is 4. Everything has to be multiplied by the 2. 2 times 3 is 6. That is your balanced equation. It's the lowest ratio that you can get because of that odd number. You can't divide that down to anything lower. Otherwise, you always want to have these are ratios, so you want them to be the lowest numbers. But you can't decrease a 7. You can't divide it by anything. It's a prime number. So that's what you do when you end up with a fraction, an odd number, a fraction. It's just steps. You do it a few times, it will make more sense. So I will do one more of those. And then that will be this from my old book. And it's very much the same as what we just did. So it's C. Oh, actually, never mind. It is the same problem. Okay. I'm just looking to see if I have another I can use as an example. No, I already have. Okay, well, that is balancing equations in a nutshell. At this point, what you have to do is just start practicing it step by step. It's very important to be very neat when you're balancing, and just take it methodically, step by step. Don't try to skip a step and do 2 or 3 at once. There's a good chance you're going to make a mistake. Do your inventory. Every time you make a change, you go back and you only need to change the side that, if you make a change on a product molecule, you only need to recount your product inventory. But recount the whole inventory. Watch for writing inventory items in the wrong atom because your order is changed. And just practice. And at the very end, always go back and double check that everything is balanced. So what you're trying to do is to get the atoms on the left side to balance the atoms on the right side. Oh, one more thing. Charges have to balance. If you have, and I can work through this at a lecture. If you have a charge, I don't have an example handy. But let's see, HCl. (3O) plus Cl negative. And this is aqueous. This is aqueous. So these have charges. In this case, let's see, it's 3. So this is already balanced, right? I have 3 hydrogens, I have 1 oxygen, and I have 1 chlorine. But this has charges. If you get a reaction let me think of one, that you end up with an imbalance of charges. Hang on, I'm going to pause and find an example. Okay, all right, I found example just at least to illustrate. I didn't write this the phases down just to try to save room, but normally you would have the phases. One hint, if you have a polyatomic ion like nitrate, it's traveling as a unit. So you can actually, you can usually track it as a unit. I'm going to do that here because I'm just trying to show you the charges. So copper, and I'm going to track nitrate as a unit and OH because they're traveling as a unit. They're never going to separate out. So when you have a charge, you have to balance your charge, just like an atom. So we put it in our inventory. So let's start out, we have one copper over here, one copper over here. I have two nitrate groups, and I have one OH group. One copper over here, I have one nitrate group, and I have two OHs. Okay, copper's fine. I'm going to start with the OH. I have two on this side and one. So I'm going to put a 2 here. Oh, I originally had one negative charge on each side, right? That's for the negative charge. Now I have just changed. So my copper is still 1 and my nitrate is still 2. Notice this doesn't have a charge because it's in a molecule. This is by itself. So I now have 2 OH groups and I have a 2 minus charge. So you're multiplying this times 2. You also have to take account of the charge. So 1 copper, 2 OH. All right, so I have a disparity now with my charge and with my nitrate. So you do the charge last, because often when you do the molecules and the atoms, you will take care of the charge, but you always double check your charge. So I need to have 2 nitrates over here. So I have 1 copper. I now have 2 nitrate groups. I still have 2 OH, and I have 2 negative. So now I am balanced. So when you have a charge in your reaction, you have got to put that on inventory. And you have to make sure that it is balanced as well. If it's not, your reaction's not correct. Okay. So that's it for now. The next lecture will be lecture 11, and that's going to be reaction stoichiometry, and that will be broken up into a couple of lectures. So go out, practice, just practice, 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 and you'll find pretty quickly it'll come to you pretty quickly. All right, have fun.